As you know, if you're in my class, we have an upcoming test, and so I created this video to review with you, and you can just kind of work through, listen to me or watch me work through the problems and check your work and hopefully clarify any questions that you might have. So first of all, if you take a look at the test review, which you also have a copy of, make sure that when you're studying that you go through and make sure that you're secure on each topic. The test review gives you the topics, and it tells you where in your packet to go and review, and it tells you some specific problems that you can go back and redo. Remember, when you're preparing for a math test, you need to have evidence. You need to show you need to actually do some work. So when you're looking at the optimization problems, make sure, let's undo that, make sure that you look at the various types of problems, because overall, to solve an optimization problem, you're trying to find the maximum or the minimum. The whole idea is to apply the extreme value theorem, and the strategy and the technique is pretty much the same for every problem, but then various problems come in types. You've got the geometry, the area, the volume. A lot of them involve geometry. So anyway, make sure you spend some time reviewing the optimization. Evaluating a definite integral by determining the area under a curve. At this point, the only way that we know how to evaluate a definite integral, and of course a definite integral is something like from a to b of f of x dx, and when you evaluate that, you get a particular value. You get a numeric value, and at this point, the only way that we're doing that is by finding area under a curve. Remember that we have used the three strategies that we have used so far that you might need on your test are counting blocks. That would be one strategy. A second strategy would be Riemann sums. Make sure you're familiar with all of these. And the third strategy would be the trapezoidal rule. So make sure you're very detailed in your study. And again, some pages in the packet that you can use to study that. Write a definite integral that represents the total area under a curve. Now in your packet there is a reading that discusses this whole idea of positive area versus negative area, and in class we have talked about how to write for the total area. So I'll probably ask you to do this with and without absolute value. So go back and take a look at that. Sketching the graph of a family of functions that share a same derivative. Remember, when you find the antiderivative of a function, and this is a general antiderivative, you get the original function plus c, which is a constant of integration, and this is the family of functions that we're talking about. And the family of functions differ by a vertical translation, so you have an infinite number of functions that share the same derivative, and some page numbers in the book that you can use to look at that. Linearization, I don't really know what to say. You're just pretty much writing the equation of a line and making some predictions, but make sure that you review it. You have in your last package, you can go back and look at that. The second derivative test to determine local extrema. Remember, if you have a critical number, priority number 1 is you have to have a critical number. Otherwise, there's nothing to test. And then you're going to substitute your critical number into the second derivative. And if the outcome is positive, you get a local minimum. If the outcome is negative, you get a local maximum. And if the outcome is 0, you can't determine anything from that. And then finally, finding antiderivatives, and these are general or indefinite, I should say, definite integrals, which is this type right here. And I will warn you to make sure that you go back and you make sure that you know the trig derivatives / integrals. You've got to know those trig ones very, very well. My suggestion would be, once you get on the test, is to go ahead and write them down. I wanted you to see that on my Edline page, in addition to this video, These are videos that you can access from Edline. They're not my videos. They're videos made by other people, but it's just more resources that you have to be as prepared as you possibly can for the test. All right, let's actually look at the test review that you have already completed. The first problem is you are to set up a midpoint sum. So we're doing Riemann sums. We're using rectangles to approximate the definite integral from 0 to 4. Do not solve. Sketch the rectangles. Well, actually, I think I do want you to solve, and I think you probably already did. So the first thing that you need to be able to do is to make sure that you can actually sketch the rectangles properly onto the graph. So if you're not quite sure when you are doing a midpoint approximation, since we have, how many rectangles did it say? 6. So you're going to take the interval, which is 0 to 4, so 4 minus 0 divided by 6 gives me 4, 6, which is 2/3. And this tells me the width, or the base, of every rectangle. So when you look at my work, you'll notice that the first rectangle stops at 2/3. The next rectangle stops at 2/3 plus 2/3, which is 4/3. So you have to use your fractions to figure out how wide the rectangles are. Then once you get determine where your rectangle is going to stop, you go to the midpoint. So this would be the middle. You go directly up to the curve. You put a dot, and you travel to the right and left, and that's how you form your rectangle. So we have our 6 rectangles in there. Now the next objective would be to actually determine the area of all 6 rectangles as an approximation of the definite integral. In this case, we don't have to worry about any negative area because the graph is completely above the x-axis. All right, so to calculate that area, in this particular case, all of the rectangles have a common width of 2/3. So in my work, you'll see that the 2/3, that's my common width. Now remember, the rectangles don't always have a common width. It just happens to be so in this problem. So the first midpoint, and all of these guys, remember, are the sum of all of the heights of the rectangles. So the first midpoint occurs at a y value. That's what we're concerned about, a y value of f of 1/3, because the x value, the midpoint, is here at 1/3. So f of 1/3 would give me the height. Then I'm going to move 2/3 of a unit away from that. So I started at 1/3 plus 2/3 puts me at 1. So that's going to be my next midpoint. So I have f of 1. Then I'm going to add 2/3 to 1, and I get f of 5/3. 2/3 to 5/3 gives me 7/3. 2/3 added to 7/3 gives me 9/3, which is 3. And 2/3 added to 9/3 gives me 11/3. And that's my last midpoint. So we're not actually going to approximate these y values, but this is the approximation of the definite integral from 0 to 4 under this particular curve. Take some time to read this whole idea about net area, when area is positive and when area is negative. And we have talked about this in class with displacement versus total distance traveled. Again, just take some time to make sure that you understand when you're going to keep the signs of the area and when you're going to force the area to be all positive. And this is just more of that reading. All right, let's jump into the next set of review problems. We've been given a table here, and in problem number 1, our goal is to approximate the area bound by this curve f of x, and this is my curve f of x, and the x-axis from 0 to 3. Use, again, a midpoint approximation. You got to read every word. 3 subintervals, and we're to write a definite integral. So let me go up to my table. I'm going to go from 0 to 3 with 3 subintervals. So this would be 1, 2, and 3 rectangles. Now each rectangle has a middle, so in the first rectangle, this would be the height of the first rectangle, the middle. This would be the midpoint. Second rectangle, that would determine the height, and the third rectangle determine the height. Do these have a common width? The first one goes from 0 to 1, so the common width, or the width there, is 1. From the next one, we're going to go from 1 to 2. We have and 2 to 3, so in this case we do have a common width. So my definite integral is from 0 to 3 of f of x dx. 1 is my common width, and 4 is the first height, 7 is the second height of the second rectangle, and 1 is the height of the third rectangle, and these were determined by a midpoint approximation, and then when you total it up you get 12. Number 2, assume that the first derivative of g is f of x. So up here in my chart where it says g of x, I can actually kind of squeeze in here that this is also g prime of x. These are first derivative values on a function g. Write the linearization. Here's your root word. We're writing the equation of a line. So the equation of the tangent line at g at x equal to 1.5. When we write the equation of a line, as you know, y minus y1, point slope, is equal to m times x minus x1. They've given us the x value of 1.5, so that's been substituted here. They've given us the y value of 4, so that's been substituted, I think negative 4, so that's been substituted here. My only job is to find the slope at 1.5. So, as you can see over here, I need to find the derivative at 1.5, which is in the chart. So the derivative of g at 1.5 is equal to f of 1.5, which is equal to 7. That came directly out of the chart, and I substitute that for my slope. And that's the linearization. That's the equation of the tangent line. In problem number 3, it's going to go back to the table, so I'll turn back in just a second. It asks us to, or tells us to estimate the second derivative at 1.5. So let's go back and take a look at that. Let me get rid of all this. There we go. So we're estimating the second derivative at 1.5. Remember, we already said that f of x is g prime of x, and we want to estimate the second derivative at 1.5. When we're estimating the second derivative, this is a table of value of first derivatives, so we're going to estimate the instant rate of change. So we're going to estimate instant rate of change by approximating with the average rate of change. So we're going to choose one value above and one value below and simply do good old-fashioned slope. So that would be 4 minus 6 over 2 minus 1. And you can see in my work, the second derivative approximation is 4 minus 6 over 2 minus 1, which is negative 2 over 1, which is negative 2. So the second derivative at 1.5 is negative. Based upon your estimate, is the original function g concave up or concave down? Well, since the second derivative is negative, the original function g would be concave down at 1.5. Next statement, does the original function g have a local max or a local min at x equal to 1.5? Well, we can't really determine that because nowhere in the table or anywhere else has it been established that 1.5 is a critical number. We don't know the, well actually we do know, and 1.5 is not a critical number. So if you look back over here, the first derivative, remember we said this is g prime of x. When you go to 1.5, since the first derivative at 1.5 is 7, then 1.5 is not a critical number, so it doesn't even have a possibility of being a local max or a local min. The point of that question is to make sure that you don't just come back to this statement over here where we said the second derivative at 1.5 is less than 0 and then assume that there's a local max. Can't be a local max because 1.5 is not a critical number. And then finally, the last thing we were asked to figure out is would an approximation of the original function at 1.505 using the tangent line be greater or less than the actual function value? Well, we already established that at 1.5 the function is concave down. Therefore, the tangent line, if the function is concave down, the tangent line would be above, and the approximation would be 2 large. So just a review of linearization. All right, next problem. In the table below, x represents the time in minutes and f of x represents the rate at which George is still eating his kettle corn, remember from earlier in the year, from the Great Frederick Fair, measured in handfuls per minute. So in the x value, this is minutes, and the y value is handfuls per minute, bearing in mind that this is a rate. Use the table above to approximate the definite integral from 0 to 10 minutes for the area under f of x using 6 trapezoids. So let's put in our 6 trapezoids. We're going to go from 0 to 10. 1, 2, these are ugly trapezoids. 3, 4, 5, 6. So those are my 6 trapezoids. I've partitioned the data. The area of a trapezoid is 1/2 of the height times the sum of the bases. So there's my 1/2 out of the formula. Let me check to see if we have a common height here, 0 to 1, 1 to, oh, we do not. So we're going to have to be careful. So the first trapezoid has a height of 1. The second trapezoid from 1 to 3 has a height of 2. 3 to 6 is 3. 6 to 6.6 is 0.6. So you can see that we have varying heights, so we're going to have to set this up individually instead of having a common height. So my 1/2 is already in my formula, so this is trapezoid number 1. This is trapezoid number 2, trapezoid number 3, number 4, and number 5. So in the first trapezoid, the height is 1, and these are the sum of my 2 bases. In trapezoid number 2, the height, sum of the bases. The height, bases, height, bases, height, bases, and then my last one. When you total that up, you will determine that George eats 44 handfuls of popcorn. Now when we do our units, remember, when you multiply handfuls per minute multiplied by minutes, the minutes divide out, telling us that George is eating handfuls of popcorn. This was a rate, and when we integrate, we lose the rate. Problem number 5. What does your answer in number 4 tell us about George? Be specific. Now, when I say be specific, I'm just saying what was the time, what were the units. So from 0 to 10 minutes, George eats 44 handfuls, there are my units, handfuls of popcorn. Number 6, the graph on the right is f of x from above. Sketch 6 trapezoids onto the graph. Now remember, when you look at the graph, it's going to extend further than 10, but we're supposed to be stopping at 10. And so if there's any confusion when you did this work, you had to put it in the context of the problem to know to stop at 10. So in this case, we're going to go from 0 to 10. So 10 minus 0 is my interval divided into 6 trapezoids. So we get 10 over 6, which is 5/3. So this is, again, we got that whole fraction thing going on. These are going to be the heights, and in this case the heights are going to be equal. The heights are going to be 5/3 of a unit. So in other words, this distance is 5/3, travel 5/3, travel 5/3, travel 5/3, etc., etc. Mainly, I just asked you to do this just to get that fraction work in and understand that the partitions don't always become integers or whole numbers. And we could set, I didn't ask you, I don't think. Let's see on the next page. I should have. It'd probably be a good idea to practice setting that up. So let's go ahead. Let me get rid of this. And I'm actually going to set up the definite integral from 0 to 10 of f of x dx. I'm going to write it down here because I'm running out of space a little bit. So the area of a trapezoid, this is what you want to keep in mind. This is kind of your target. This is the geometry formula. So there's my 1/2. In this case, we had a common height, we said, of 5/3. multiplied by the first base is used once. So the first base would be f of 0. That's how tall the first base is. The second base is used twice, so we have 2 times f of, and the first, is 5/3. Remember, we're traveling 5/3 of a unit to get to the next endpoint, plus 2 times f of, and let me move this out of the way. So 5/3 plus 5/3 gives me 10/3, plus 2 times f of 15/3, which of course I can write as 5, plus 2 times, add 5, 20/3 f of, 20/3, plus 2 times f of 25/3, plus 2 times f of, no, we're down to the last endpoint, so that's only going to be once. Get rid of that. So we're down to the last endpoint, so it's used once. So f of 30/3, which is 10, so I know that I'm at the end. And I'm not going to approximate those, but that's how you would set up the trapezoidal approximation. I think it'd be worthwhile to take a look at that. All right, let's go on. Using the graph that we had below, decide if a right endpoint approximation would overestimate or underestimate the area. So we want to go back, and I'm going to flip back to the page in just a second, a right endpoint approximation. Now, there are a couple of ways to figure that out. An easy way is just to go back to the graph, a right endpoint approximation. Let's clear the board here and actually do a right endpoint approximation. So I'm going to use the graph that I have already, but I'm just going to, I'm going to ignore the trapezoid. So I'm going to go to the first right endpoint and make a dot and travel over. To the next right endpoint, dot on the curve and go over. To the next right endpoint, over, down. To the next right endpoint, over and down. To the next right endpoint, over and down. To the next right endpoint, over and down. So when you look at that, you can see that we lost, but everywhere else we're gaining, and we can clearly see that we're gaining more than we lose. So a right endpoint approximation would be too large, and the reason that happens is because this curve is concave up, and that forces the rectangles to be outside. A left endpoint approximation would be too small, and again, you can draw the graph to actually see that. Problem number 8, if f of x, going back to the same problem we were before, this function that you see, and this is the function that corresponds to the table that we have right back here. So if this function represents the rate at which George is eating, find the function h of x that indicates the amount of popcorn eaten if George had eaten 5 handfuls of popcorn at x equals to 0. So bear in mind that this function is a rate. It's George's popcorn eating rate. And we're trying to go back to the function that tells us how much popcorn he had eaten. So we need to find the antiderivative of the rate. So h of x would be the antiderivative of f of x. So we're going to use the power rule to get the function, and then when we get the original function, we have a plus c because we have our general antiderivative, which is a family of functions. And so in this problem, they gave us an initial condition. They said at time 0, George had eaten 5 handfuls of popcorn. So I substitute 0 in place of x, solve for c. C turns out to be 5. And so I write my equation. This is the particular function, that represents how many handfuls of popcorn that George is eating. And then finally, problem number 9 is an optimization problem. We have a cylindrical can. It has a closed bottom and an open top. Very important to read the question. Open top. So I'm not going to include that. It's made from two kinds of material. The material used to make the bottom of the can costs 5 cents per square inch, so bottom 5 cents per square inch. Material used to cover the surface, and the surface, when they talk about the surface, they're talking about the curved or the round part of the can. That costs 3 cents per square inch. The total cost of the can is no more than $7.35. Find the dimensions of the can with the greatest, so our objective here is to maximize volume. And I actually have that over here. So my goal is to maximize the volume. The surface area of the can, now notice that since it's an open top, I have 1 pi r square, not 2 pi r square. The surface itself, remember how we talked about before that the surface of a can is a rectangle that's been rolled up. So this is the height of the rectangle. This is the base of the rectangle. But when you roll that up, that becomes circumference, and you get 2 pi r. So 2 pi r h is the surface. The cost of the can is 5 cents. Remember, they said this is how much it costs you to make the bottom, because that's out of one material. And this is how much it costs you to actually make the surface. So this is the bottom cost, and this is the surface cost. And they said the can, they can spend $7.35 on that can. So this is my helper equation, because my goal, remember, is to maximize the volume. The volume of a can is pi r square h. So I need to get rid of one of those variables, and since r is squared, I'm going to solve my equation for h. That would be the easiest variable to solve for. So I subtract 0.05 pi r squared to the left, and then divide by 0.60 pi r. Now this is not hard, it's just a little bit messy. And this would be certainly a calculator-friendly problem with all the decimal values. So I'm going to substitute that into my volume equation. So volume is equal to pi r squared. I'm substituting this in for h. Again, it's messy, but that just means you have to be careful. Then I divided out a pi, and I divided out one of the r's with an r in the denominator, and then I distributed the r, and that's how I got to this step right here. Alright, then I actually multiplied, I got rid of my decimals, I multiplied the numerator and the denominator by 100, so that's how I got 735 over 6. I also split my fraction up into two fractions to make it easier to find the antiderivative, and that's where I got 5/6 pi r cubed. Then I took the derivative by the power rule. So all I did here is use the power rule. I didn't try to use any kind of quotient rule or anything like that. Then I set the first derivative equal to 0 because I'm looking for my critical numbers. So that's what's going on in this particular step. I'm solving my equation. Again, it's not hard. It's just got fractions in it. So I isolated r squared. And then to get r by itself, these steps right here, I'm just cleaning up my fraction. To get r by itself, I take the square root. So actually, we didn't need a calculator at all, except if I'm going to calculate h not as an exact value. And I get 7 over the square root of pi as the radius. And then to find the value of h, I would go back up here with the 7 over square root of pi changed to a decimal number. And I would substitute that in place of r and use my calculator to get the height to be 6.58 inches. Now, again, I don't want you to look at this problem and think it's difficult. It's really not a difficult problem, but it has fractions and decimals, and the key is to be careful and not let algebra end up kicking your butt. Alright, so I hope that you're able to use this video to help get you ready for your test or to answer any questions that you might have.